In part A, we're asked for what is the induced EMF as the front of the wire goes into the magnetic field. Well, we know V0, we know how much wire is going to be moving in, that's the height h, and we know the force of the magnetic field, that's B, out of the page. What we do know is that flux equals the integral of B dot dA, and that if we derive that, we get d flux over time, which then would equal, after deriving that, B times dA over time, or dt, which will ultimately equal our EMF induced. So dA d-time, or dA dt, equals our velocity, which is our change in area over time, or our change in the length for meters, times the other length. Length times length equals area, and then velocity over seconds, that's our time. So what is our L? Our L equals h. What does our V equal? Our V equals V0, and what does our B equal? Our B equals B. When you put all those together, we get our EMF induced equals B times H times V0. Moving on to part B, we're asked, what does I equal? Well, we know that V equals IR, and well, what's our V? Our V equals E induced, and our EMF induced equals BH times V0. So, if V equals IR, we know that I equals V over R. R equals, well, R. So when we substitute in what we have for V, we get I equals B times H times V0 over R. So ultimately, I equals BH V0 over R. In part C, we're asked, what is the direction of the current induced as it's moving in? I apologize for that. Well, we know by Lenz's law that it's the magnetic field that is going to be induced will want to resist the change of the current magnetic field. So if we know that one magnetic field, or the magnetic field that's currently there, is going into the page, out of the page, then we know that the magnetic field induced will have to go into the page. Using right-hand rule, we see that it goes clockwise, and that's our answer. For part D, we're asked, give V as a function of time. Well, we know that A equals dV dt, and we can find force relatively easily. Why? Because force equals ma. A, once again, equals dV dt. And this also equals the magnetic force, which is I times L cross B. Our L, once again, will equal H. Our B equals B. And then, what does our I equal? Well, if we go back to part B, we remember that I equals B times H times V0 over R. So we put that all in, and ultimately we get M times dV dt, or A, equals B times H times V0 over R, times H times B. Then simplifying that, we get B squared H squared V0 over R equals M dV dt. We bring the things over, and we have an integral here. We have the integral from 0 to t of b squared h squared over rm dt equals the integral from v0 to v of 1 over v dv. When you take the integral, we get ln of v minus v0 equals b squared h squared t over rm. Simplifying, we get this. And once we put it in terms of v, we get this, and finally, after algebraic manipulation, we get v of t equals v0 times e to b squared h squared t over rm. That's its exponent. Finally, we have part E. Part E asks to graph the velocity of the wire as it's moving in and out of the field. Well, we know that the only thing that's going to change the velocity is a force, and the only force that is applied is IL cross B. We know that I is relative to V, and we know that I changes when there is an EMF induced. Well, we know that there is an I when EMF is induced. When is EMF induced? EMF is induced when there's a change in flux. Remember this? I apologize for the handwriting. But we know that the change in flux only happens when it's entering or exiting, having a change in magnetic field or a change in area. As we look back at part A, the change in area. So let's take a look at this. So when time equals 0, it's just entering the field. Since there's a change in area here, the force is going to be pushing back on the wire, and therefore it's going to slow down the velocity. From T1 to T2, the entire wire is submerged into the magnetic field. So there's going to be no change in the area in which is consumed by the magnetic field. Therefore, there's no change in flux, therefore there's no induced EMF, therefore there is no I, therefore there is no change in velocity. Moving on between part T2 and time T3, we see that it's exiting. At this time, there is in fact a change in area. This change in area is now because part of the object is actually leaving the magnetic field. Therefore, the force will be acting on it again, and it's going to be pushing. And then finally, between T3 and T4, the object is completely out of the magnetic field. There's no change in magnetic field, therefore there's no EMF, no current, no change in velocity or force, and it just simply coasts afterwards. That is part E, and that is the entirety of this problem.